Higher Physics Practice Prelim, Electricity in Our Dynamic Universe, Section 2 questions. In this question, a shot put is an athletics event in which competitors throw a shot as far as possible. The shot is a metal ball of mass 4.0 kilograms. One of the competitors releases a shot at a height of 1.8 meters above the ground and at an angle theta to the horizontal. The shot travels through the air and hits the ground at x. The graph shows how the release speed of the shot v varies with the angle of projection theta. Here's a better picture of the graph. The angle of projection for a particular throw is 40 degrees. Part 1, Part A state the release speed of the shot at this angle. For this, we simply need to read off the graph 40 degrees at x, follow the line up, and at this divisions we have 4 divisions above the 10 line. Each of the divisions represents 0.4, giving us a value of the b to be 11.6 meters per second. Part 1, Part B, calculate the horizontal component of the initial velocity of the shot. The horizontal component of velocity can be found using VH is equal to V cos theta. In this example, V is 11.6. Theta is equal to 40 degrees as stated in the question, giving us a value of 8.9 meters per second. 1 mark for this. In Part C, we're asked to calculate the vertical component of the initial velocity of the shot. For the vertical component, we use VV is equal to V sine theta, which again is 11.6 multiplied by sine of 40, giving us a value of 7.5 meters per second. In Part 2, we're told that the maximum height reached by the shot is 4.7 meters above the ground, and the time between release and reaching this height is 0.76 seconds. So we've told the first part of the journey, and in order to find the total time between the shot being released and hitting the ground, we need to find out how long it takes for the shot to move from its maximum height to the ground. So when we're at the maximum height, our vertical velocity is 0. So u in this question is going to be equal to 0. We know the height through which the shot is falling, so s is equal to 4.7 meters. We know acceleration due to gravity. Remember, the shot is going from its maximum height to the ground, so gravity is going with us, so it's a positive 9.8 ms to the minus 2. And we want to find the time. This leads us to use the equation S is equal to ut plus 1/2 at squared. 4.7 is equal to 0 because u is equal to 0, plus 1/2 times 9.8 times t squared. We can rearrange this and say that t squared is equal to 4.7 divided by half of 9.8, which is 4.9. T is equal to square root of that, giving us a value of time of 0.979 seconds. So this is the time taken from the shot to get from its maximum height back to the ground. In order to get the total time, we need to add on the time it's taken for the shot to get to its maximum height. So that's the 0.76 seconds. So our total time is going to be equal to 0.98. We'll just round that to 2 decimal places, same as the 0.76, plus 0.76, giving us a total of 1.7 seconds, sticking with the same two significant figures. There is an alternative method for this, calculating the final velocity v first, and then applying v equals u plus at, but this is the simplest method. In part B, we're asked to find the range of the shot for this throw. So the horizontal range can be calculated using d is equal to v times t. Remembering your v here is your horizontal component of velocity. Now we calculated our horizontal component of velocity previously, and that was found to be 8.9 meters per second. So the horizontal range, d, is equal to 8.9 multiplied by the total time we calculated, which is 1.7 seconds, giving us a value of 15 meters. Part B, using the information from the graph, explain the effect of increasing the angle of projection on the kinetic energy of the shot at release. Well, we can see from the graph that as the angle of projection increases, the velocity of release speed is going to decrease. And this is because within any system, we only have a certain amount of energy to use. When we lift up the shot to a greater height in order to release it at a greater angle, then the amount of energy we need is going to get larger. If we increase the amount of energy we need in order to lift the shot, then there's going to be less energy available to convert to EK. So to get the marks of this question, we have to say the greater the angle, the more energy is used to lift the shot put to a greater height, and so there's less energy available for kinetic energy. And it kind of makes sense. The higher up you are trying to project the shot, the harder it's going to be in order to project it at velocity. Okay, so in this question we have a crash test dummy within a crash car. We're told that the force applied by a seatbelt on a crash test dummy is being investigated. The crash test dummy is placed in a car. The car then travels along a test track at a speed of 13.4 meters per second. It collides with a wall and then comes to rest. State the law of conservation of linear momentum. Okay, so the law of conservation of linear momentum has two parts. First of all, we say that with any closed system, the total, and you have to have the word total, the total momentum before a collision is equal to the total momentum after, that's the first part, in the absence of external forces. The most common mistake made with this question is forgetting the total. Second most common would be forgetting in the absence of external forces. You have to have both the total and the external forces in order to get the marks. Okay, so in the second part of question 2, remember we have our car traveling on this track at a speed of 13.4 meters per second and then collides with the wall. The key word here is the word rest. We're told the mass of the car and the dummy is 1200 kilograms. Our initial velocity is 13.4 meters per second, and our final velocity is 0 because we come to a rest. So our change in momentum, delta mv, is equal to mv minus mu. Now we've got a negative sign here. We're taking two different multiples, two different products from each other. It's a good idea to use our brackets. So 1200 multiplied by 0 minus 1200 multiplied by 13.4 gives us a value of negative 16080 kilograms ms minus 1, or we could say negative 1.6 times 10 to the 4 kilograms ms to the minus 1. Now, the most common mistake made here is mixing up your v's and your u's. If you mix up your v's and your u's, then you're going to end up with a positive value for the change of momentum. But that would suggest that the speed of the car has increased, but it hasn't. The speed of the car has decreased, so we expect the change of momentum to be negative. All right, so in part B, we still have our car travel along the test track at 13.4 meters per second, collides with the wall and comes to rest. We've calculated the change in momentum, and now we're on to part C. Crash test dummy has a mass of 75 kilograms and is wearing a seatbelt. So let's write that down. M is equal to 75 kg and travels a distance of 0.48 meters. So that's our displacement. S is equal to 0.48 meters. So there's two ways to go about this question. Either we could go down an energy route and compare our EK to our work done, or we could use equations of motion and then use F equals ma. I'm going to go for the equations of motion method, but I'll write down the equations for kinetic energy and work done anyway on the other side. So if you wanted to, you could work out the alternative method. So v squared is equal to u squared plus 2as. Our final velocity is rest, so that's 0, is equal to 13.4 squared plus bracket 2 times our acceleration times 0.48. So 0 is equal to 13.4 squared plus 2 times 0.48 is 0.96 a. A is equal to negative 13.4 whole squared divided by 0.96, giving us a value of negative, as we expect for slowing down, 187.04. Now, I'm given this as a number of different significant figures, that's 5 sig figs, because this is an intermediate step, and I don't want to introduce an intermediate rounding error. Now that I've got the acceleration, I need to apply F equals ma. So the unbalanced force that had to have acted on the crash test dummy in the car in order to slow it down is equal to the mass, which we're aware is 75 kilograms, multiplied by the acceleration, which is negative 187.04. This gives a value of negative 14,028 newtons, or 1.4 times 10 to the 4 newtons. Now, the question's asking for the average force exerted on the dummy by the seatbelt. So having the negative number here as a negative is absolutely fine, but it would also be acceptable simply to have that as 1.4 times 10 to the 4 newtons. You don't need to show direction as it's implied. In part D, we're told that the seatbelt is designed to stretch slightly during the collision. Explain in terms of forces and advantage of this design. This is a very, very common question dealing with impulse. If the seatbelt stretches slightly during the collision, we can say that the time of collision is going to increase, remembering that impulse is equal to our change in momentum. So if the time increases and the change of momentum stays the same, because change of momentum is constant, that means the average force acting is going to decrease. So we increase the time of collision, which then decreases the average force. And in order to get all the marks here, you'd have to mention about the impulse being equal to the change in momentum. In question 3, we're told about a car that's traveling on a straight, level road. The brakes are then applied and the car comes to rest in a distance of 50 meters. Again, we have that keyword rest. Just underlining my values here. We're told that the work done in stopping the car is 75 kilojoules and the average external frictional force exerted on the car is 300 newtons. The total mass of the car and driver is 1100 kilograms. Calculate the average force exerted by the brakes on the car. Okay, so let's get all our information down. EW is equal to 75 kilojoules, 75 times 10 to the 3 joules. And we're told that our distance traveled is 50 meters. We use our equation for work. EW is equal to FD. 75 times 10 to the 3 is equal to our force multiplied by 50. Therefore, our force is equal to 75 times 10 to the 3 divided by 50, which is 1500 newtons. But remember, 1500 newtons is the total force that needs to be applied over the distance in order to bring the car to a rest. Not all of that force is being provided by the brakes. Some of that force is also being provided by the external frictional force in the question, which is 300 newtons. So the force from the brakes is going to be equal to the total force take away the force from the friction. So that's 1500 take away 300 newtons coming from the friction gives us 1200 newtons. In part B, we're told a second car of a smaller total mass is traveling at the same speed along the same road. Its brakes are applied and it stops in the same distance of 50 meters. The same average external frictional force is exerted on the car. How does the value of the average braking force on this car compare to that of the original car? And you have to justify your answer. So justifying your answer means that you have to show a relationship or an equation. And because this is a must justify, that means you must show that justification. So because we have a total mass which is decreased, we can say that our kinetic energy, the kinetic energy of the car, is less. So the initial kinetic energy of the car is going to be less, which means that the work done, the EW, in slowing the car down is also less. Now, assuming we have the same stopping distance, that's 50 meters, that means the average force, or the total force, is less. And also assuming that the same frictional force is acting on the car, that is 300 newtons, that means the force required from the brakes is also less. Your justification there is by having the relationship between EK and EW. Question 4. A student carries out an experiment to measure the universal constant of gravitation. The apparatus consists of a horizontal rod with small lead spheres at each end. The rod is suspended from its center by a thin torsion wire. The student places a large lead sphere near each of the small spheres. The gravitational attraction between each pair of large and small spheres causes the torsion wire to twist. The angle of the twist is indicated on a fixed scale by the position of a pointer attached to the rod. We're told that the torsion wire twists by 1 degree when each small lead sphere experiences a force of 1.56 times 10 to the negative 9 newtons. In A, Part 1, we're told that the student measures an angle of twist to be 0.45 degrees, and we're asked to show that the gravitational force between one pair of large and small spheres is 7.0 times 10 to the negative 10 newtons. So if 1 degree twist, we have a force of 1.56 times 10 to the negative 9 newtons. For a 0.45 degree twist, we have 0.45 multiplied by 1.56 times 10 to the negative 9, which gives us a value of 7.0 times 10 to the negative 10 newtons as required. In Part 2, we're told the mass of each of the lead spheres. The small lead sphere has a mass of 0.048148 kilograms, so M1 is equal to 0.0148 kilograms, and the large lead sphere has a mass of 1.52 kilograms. The student then measures the distance from the center of the mass of each of the large spheres to be 46.5 millimeters. So that's our radius. R is equal to 46.5 millimeters. We don't like millimeters, so that is 46.5 times 10 to the negative 3 meters. What value does a student determine for the universal constant of gravitation from these results? Well, our known equation is F is equal to G M1 M2 over R squared. So we're effectively rearranging for G here. So I can say that G is equal to F over M1 M2 over R squared, which is the same as saying G is equal to F R squared over M1 M2. So that means G is equal to our force, which we've just calculated in the previous question. That is 7.0 times 10 to the negative 10 multiplied by our radius squared. That's 46.5 times 10 to the negative 3 squared divided by our mass product 0.0148 multiplied by 1.52, giving us a value of 6.7 times 10 to the negative 11 meters cubed, kilograms to the minus 1, s to the minus 2. Now that is a really difficult unit to remember. However, if you have a look at the data sheet at the front of your paper, you're given the actual value of the gravitational constant, which also contains the units. In Part B, we're told the manufacturer of the apparatus claims that this experiment can achieve an accuracy to within plus or minus 2.5% of the accepted value for the universal constant of gravitation. Does the student's value for the universal constant of gravitation agree with this claim? You have to justify your answer via calculation. It's a must justify, so no justification, you don't get the marks. So we should know the value of G coming from the data sheet is 6.67 times 10 to the negative 11. So what we've got to do is find out what's plus or minus 2.5% of that. So 2.5% of that is 2.5 divided by 100 multiplied by 6.67 times 10 to negative 11, which gives us a value of plus or minus 1.7 times 10 to the negative 12. Another way to express this would be 0.17 times 10 to the negative 11, which is handy when we're coming to compare the values to the known value of G. So in order for the claim to be valid, we have to land in between 6.50 times 10 to the negative 11 to 6.84 times 10 to the negative 11. Now our value is within range because our value that we calculated is 6.7 times 10 to the negative 11. So it's within the range. In the last part of the question, we're told that the student now decides to replace the pointer on the horizontal rod with a small mirror. A laser beam is then directed at the mirror in such a way that the beam is reflected onto the scale as shown. Explain how this modification improves the accuracy of the experiment. Okay, so remember, the accuracy of the experiment is about how true we are to the actual value. If we're using a laser pointer as opposed to using the pointer attached to the steel rod, we're going to end up with an increased accurate reading, an increased reading on the scale. That means we have a decreased value of the reading uncertainty and a decreased value of the reading uncertainty means we have a smaller percentage uncertainty. Now, the smaller our percentage uncertainty, the more confident we can be that our value is close to the accurate value.